So let's talk a little more about Faraday's law. And between Faraday's law and Lenz's law, there's a couple of things going on. Uh, there's not just one coil with a magnetic field that's happening here. There's actually two magnetic fields involved in one coil. So we have the magnetic field due to the um, current in the coil, and we have the magnetic field due to the induced current in the coil. So the current is being produced by an outside source, and the induced current is being created due to the change in flux and the opposition. And this is a good thing for this to happen because in capacitors, have a limiting mechanism, and that's the electric field. So once the electric field gets strong enough to oppose the charges uh, being able to produce or to put themselves on the plates, the current stops. In the inductor, inductors have a limiting mechanism, and that's the induced magnetic field. And that keeps the current from continuing to increase infinitely, and for the magnetic field to not increase infinitely. So these ideas of limits really keeps the world under control. Now, Faraday's law is has an interesting uh, way of looking at it. So I'm going to write it up here because I'm running out of space. So I'm going to write it again. E equals negative n times the different derivative of magnetic flux with respect to t. And I can write this in a couple of different ways. I can write this as a constant with my magnetic field changing, or it can be written with a magnetic field constant and the area changing, and in a completely difficult way is if both the magnetic field and the area is changing, and then we'll just go back to this formula to indicate that. But you can see that we can either change the magnetic field or we can change the area, and we can produce the same or similar results. So in this case, where we spin the coil, we are changing the flux by changing the amount of magnetic field through this area. Because in this area, the magnetic field is perpendicular to the surface or is parallel to the area vector. So it's a maximum, and then when I turn it, I've now taken all the flux out because the area vector is perpendicular to the magnetic field, be going in this direction. Or I can say that the surface is parallel to the magnetic field. So we can induce a potential that way. The other way we can do it is to take and change the area. So I'm not changing the orientation with the area vector and the coil and the magnetic field, but I'm stretching the coil, I'm changing the area, and I'm going to induce a current inside the coil because I've changed the area. So we see that the left-hand picture would go with the top equation there, and the right-hand picture would go with the bottom equation. So there's two different mechanisms that we can use to induce a potential, induce a current inside of a coil.